Hello everyone, welcome to another lecture of the course Digital Signal Processing. In the previous lecture, we have introduced the designing of ideal low-pass filter, and we have seen that the typical frequency response for the ideal low-pass filter is given something like this. So for that, the magnitude of the filter is 1 for all the range of frequencies ranging from minus omega c to omega c, where this omega c is nothing but the cutoff frequency, and it is 0 for all the other range of frequencies that lie out of this desired range or the desired pass band. And the time domain equivalent of this filter or the low pass filter was obtained as h of n is equal to sine of omega c n upon pi n for n equal to 0, whereas it was obtained as omega c by pi for n equal to 0, and we have said that this is nothing but a sinc function. And if we visualize it graphically, it looks something like this as shown in this figure. So this is the typical sinc function representation in the time domain. Now let us analyze this sinc function more. So this is the time domain representation of our ideal filter, and we can see that this ideal filter ranges from all the way from minus infinity to infinity. So suppose the ideal filter is given as, say, h ideal of n. So we say that this ideal filter ranges from all the way from minus infinity to infinity, and hence this is of infinite duration. So this ideal filter is of infinite duration. Now other thing that we can observe is this filter, it has non-zero values from minus infinity to 0, or it has non-zero values for n which is less than 0, and hence this ideal filter is non-causal. So this ideal filter is non-causal. But can these non-causal systems be made causal systems? Let's check it by a simple small example. So for that, what we are going to consider is h hat of n, which is given as 1, 2, 3, and this 2 is located at n equal to 0. Now we can observe that we have a non-zero value, that is 1, for n equal to minus 1. And hence this filter or this system is non-causal. Now suppose I shift this h hat of n by 1 unit or introduce a delay in this system of 1 unit. So what we have is h hat of n minus 1, which is equal to the same sequence 1, 2, 3, but now this 1 is located at n equal to 0. And we observe that there is no finite or non-zero values for the value of n which is less than 0, and hence this system is causal in nature. So by introducing a simple delay, we can make this non-causal system a causal system. So we can have the same thing in the case of this ideal filter. But now this ideal filter is basically of infinite duration from minus infinity to infinity, and in that case, in order to have it from 0 to infinity, so in that case we will need to introduce a delay of infinite duration. So to make it causal, we require an infinite delay. And this thing is highly impossible, and therefore this ideal filter cannot be made causal. Now suppose we make this ideal filter somehow of finite duration, so we can eliminate these two problems which we have in this ideal filter. So basically what we do is we limit the range of this ideal filter or make this ideal filter truncated to a finite duration. So suppose I have my ideal filter that is given as H ideal of n. So what we do is just we truncate this ideal filter to obtain a filter, say h of n, which is of finite duration. So this h of n is of finite duration. So by this truncation, we can convert this infinite duration signal or system to a finite duration system, and we say that this truncation is a symmetrical one. So let's see how exactly it is done. So let us consider this example of the ideal filter. So by truncation, we will consider only a limited set of values from this filter, say the value which is located at n equal to -1, n equal to 1, as well as at n equal to 0. So by truncating this ideal filter, we consider the value of filter only at locations n equal to -1, n equal to 0 and n equal to 1. So what we have is simply a sequence which is given as H ideal of n that is located at -1, then H ideal of 0 and H ideal of 1, and this H ideal of 0 is again located at n equal to 0. So what we have is a finite duration signal, a finite duration impulse response, which is nothing but this h of n given as a sequence that is h ideal of -n, h ideal of 0, h ideal of 1, and since this system response is of finite duration, we call such type of system as finite impulse response system. So this system is known as finite impulse response system or FIR filter. So now the system which we have is h of n, which is equal to a sequence of h ideal of -1, h ideal of 0 and h ideal of 1, and this h ideal of 0 is located at n equal to 0. And if we find its z transform, so what we have is h of z is equal to h ideal of -1 into z plus h ideal of 0 plus h ideal of 1 into z to the power minus 1. So now let us take this z common from the entire equation. So what we have is z into h ideal of minus 1 plus h ideal of 0 into z to the power minus 1 plus h ideal of 1 into z to the power minus 2. Now if we observe this equation, this entire thing inside the bracket, we can say that we have three zeros or three finite zeros. By finite, we are excluding the zeros that are located at z equal to 0 as well as at z equal to plus minus infinity. Moreover, if we observe it carefully, we can say that we have 0 finite poles. And the systems which have only finite zeros are referred as all zero systems. So this h of z is of FIR system or a FIR filter, as well as it is all zero. It is all zero filter. So now we have a finite duration system or an FIR filter, and ideally what we require is a frequency response something like this. So this is nothing but the ideal or the expected magnitude response of the filter. So after truncating to 3 samples, that is what we have considered only is for n equal to minus 1, n equal to 0 and n equal to 1, the frequency response is obtained something like this. So this blue one is nothing but the frequency response for the truncated version, whereas this one is the ideal one. So we can observe that there is a quite huge deviation in the expected or the ideal one as well as the obtained one after truncation, and we can see that the length of this filter is simply 3, which is quite short. So let's see what happens if we increase this length. So now the length is 51, and hence this filter will have finite values or non-zero values for n equal to minus 25 to 25. And if we observe this filter here, we can see that it is quite similar to the rectangular filter or the low pass filter, that is the ideal one, but we can observe some kind of ripples at this point as well as at this point of discontinuity, and hence we are observing ripples. Now let us increase the number of points or the length of the filter further. So now the length is 101, and hence the filter will exist for n equal to minus 50 to 50. Now again, this frequency response is quite similar to the ideal one, but still we have some kind of ripples that are present at this point as well as at these points of discontinuities. So what we can see is this truncation or the sudden truncation for the ideal filter leads to ripples in the frequency domain. So sudden truncations of ideal filter leads to ripples in the frequency domain, that is in h of omega. And this typical phenomena is referred as Gibbs phenomena. But even though we have these ripples in this passband as well as this attenuated band of frequencies, we can still have a causal filter. So let's see how. So now after truncation of this ideal filter, what we have is h of n, and let's say we have the length of this filter given by L. So this L is nothing but the length of the filter, and if its length is n, then this h of n basically is non-zero for minus of L minus 1 by 2 to L minus 1 by 2, and this is nothing but the range of n. For example, we had considered the 3 length filter, that is L equal to 3, and in that case the n value was from minus 1 to 1, where this 1 is nothing but L minus 1 by 2. Now if we shift this h of n by L minus 1 by 2, we can eliminate this minus of L minus 1 by 2 to 0 samples, that is the samples that are existing for minus of L minus 1 by 2 to 0, by simply shifting it to 0 to further values, and these samples are basically responsible for making this h of n a non-causal. So by shifting this h of n by L minus 1 by 2 units, we can make its range from 0 to L, which is nothing but a causal system. So this h of n minus L minus 1 by 2 basically exists for n equal to 0 to L minus 1, and hence this is a causal system. So let us go back to the example which we had seen earlier. So the truncated version of our filter was like h ideal of minus 1, h ideal of 0, and h ideal of 1. And if we represented it graphically, so suppose this is my n-axis. So we had the values at n equal to 0, then at n equal to minus 1, and at n equal to 1. So this is nothing but our h of n, and this is our n-axis, and the length of this filter L is nothing but 3, and the value L minus 1 by 2 is nothing but 1, and suppose I shift it or introduce a delay of 1 unit. So what I am left with is something like this. So again, this is the graphical representation, this is my n-axis, and now after shifting it by 1 unit or introducing a delay of 1 unit, the value which was present at n equal to minus 1 will be basically available at n equal to 0. So the value which was present at n equal to minus 1 is now available at n equal to 0. The one which was available at n equal to 0 is now at n equal to 1, and the one which was at n equal to 1 is now at n equal to 2. So now this value which was present at n equal to minus 1 is at n equal to 0 after shifting. So this is nothing but h of n minus 1. The one which was at n equal to 0 is now at n equal to 1, and the one at n equal to 1 is now at n equal to 2. So this original system, this h of n, is basically a non-causal system. So this h of n is non-causal, but by shifting it by a unit or a length of L minus 1, or by introducing a delay of length L minus 1 by 2, what we have is a causal system. So the claim that we had made, that by shifting this h of n, or the truncated version, by a L minus 1 by 2 units, will result in a filter that has values from n equal to 0 to L minus 1, and hence we get a causal system. Now suppose this h of n minus L minus 1 by 2 have the coefficients as b0, or be represented by a sequence, say b0, b1 and so on up to b of L minus 1. So this is nothing but a sequence that exists from n equal to 0 to n equal to L minus 1. So this exists from n equal to 0 to n equal to L minus 1, and whereas this b0, b1 and so on till b of L minus 1 are nothing but the filter coefficients. Now if we find the Z transform of this system, so what we have is h of z is equal to b0 plus b1 z inverse and so on up to b of L minus 1 into z to the power minus of L minus 1. So this is nothing but summation of k running from 0 to L minus 1 into bk into z to the power minus of L minus 1. So what we have is h of z is equal to summation k running from 0 to L minus 1 bk into z to the power minus of L minus 1. So let us substitute this L minus 1 by m. So what we are left with is h of z is equal to summation k running from 0 to m bk into z to the power minus k. Sorry, this factor here should be z to the power minus k, and same thing will be here also. So this factor in the exponent of this z will be nothing but z to the power minus k. So what we have is h of z is equal to summation k running from 0 to m bk into z to the power minus k. So now if we observe this equation carefully, we can say that this equation is nothing but a polynomial of variable z inverse of degree or of order m, and hence this m is referred as the order of the filter. So this m is nothing but order of the filter, and this length of the filter is given as m plus 1, that is order plus 1, and this equation h of z is nothing but a standard format or the standard representation for Z transform of a causal and FIR system. So in this lecture, we started by considering some faults or some issues that are with the ideal filter, and we said that this ideal filter is of infinite duration. That is, we said that it exists from n equal to minus infinity to infinity. And since it exists from minus infinity to infinity, it has non-zero values for n less than 0, and hence it is non-causal. We have also seen that this ideal filter cannot be made causal, because for making it causal we require infinite amount of delay. So if we eliminate this infinite duration thing, we can make this non-causal system a causal system. So we truncate this ideal filter to get what we call as a finite length filter or a finite impulse response filter, which is referred as an FIR filter. Then by truncating this filter can be made a causal system by introducing some amount of delay. Then we have also seen the causal FIR filter's standard representation for Z transform, which is given as h of z is equal to summation of k running from 0 to m b of k into z to the power minus k. This factor should be minus k, where these bk's are nothing but the filter coefficients. This m is the order of the filter, and this L, that is given as m plus 1, is nothing but the length of the filter. Now by truncating this filter, we are compromising with the ideal nature of its magnitude response or the frequency response, and this truncation of ideal filter introduces ripples in the frequency domain, and this is nothing but the Gibbs phenomena. Now in the subsequent lecture, we are going to see how to deal with these ripples in the frequency domain, and we are going to see how we can reduce these ripples in the frequency domain by some techniques. So till then, let's stop here. Thank you.